Today I want to give you a full guide into factoring in the form of ax squared plus bx plus c when a is equal to 1. Now this could take another form when a is greater than 1, so a scenario which would be like 3x squared plus 4x plus, I don't know, like 20, let's say. That is going to be a different scenario than what we're going to look at here. Now there are going to be some scenarios in this video where we're going to look at values of a greater than 1, but there's going to be some methods that we could use to create this coefficient being a 1, and then we're going to factor it this way. So when we have this form of a trinomial in ax squared plus bx plus c, and we have a is equal to 1, what we want is we want two numbers that multiply to 12 and add up to the middle number. So we want two numbers that multiply to c and add up to your b term. So in this first example that we have, we want two numbers that multiply to 12 and add up to 7. And throughout this whole video, we're going to look at a lot of different scenarios when, what if our multiplication, we want it to be negative, but we want it to add up to a positive, or the other way around, or what if we want it to multiply to a positive, but add up to a negative. So the more you just keep practicing with factoring, the more you start to see some patterns developing and things to look for when you're trying to determine what it's actually going to factor to. So what we want our end goal to be is two terms. This is x squared, so this is going to be an x, and this is going to be an x. Because when we go back through and multiply this out, this would be x times x, which would be x squared, and then we do x times this term, and then whatever this term is times x, and then that's going to give us our 7x, and then these last two terms are going to multiply to 12. So that's why we're using this idea of two numbers that multiply to our c term, and then add up to that middle term, because if we were to multiply these binomials out, it would get us right back to where we started. So if this was like y or something, just some variable, z squared, any sort of variable really, the first term would be the x times x or z times z. And we'll look at some scenarios also with variables when like this might have a variable at the end. Okay, so in this problem we want two numbers that multiply to 12, add up to 7. And starting off with factoring, it might not be the worst idea to just like think about, all right, two numbers that multiply to 12 could be 6 and 2, 4 and 3, 12 and 1, just so you start to see, like, all right, here are my common factors that multiply to 12, and then the more factoring you do, then you'll start to notice, like, well, if I want to add up to 7, that's going to be 4 and 3. So if I go through and say 6 and 2 multiplies to 12, cool. But 6 plus 2 adds up to 8. So no, that's not what I want. I want to add up to 7. 4 times 3 is 12. 4 plus 3 is 7. There it is. And we want it to multiply to a positive and add up to a positive, so we don't have to worry about the signs. And if we check this one, 12 times 1 is 12. 12 plus 1 is 13, so that one doesn't work. King Kong just fell over. So we're going to have x plus 4 and x plus 3, because positive 4 and positive 3 were my two factors that work. And if you want to, and this will probably be one of the only times, but I'm just going to show you, if we multiply this out, x squared plus 3x plus 4x plus 12, 3x plus 4x, x squared plus 7x plus 12. There it is. And if you want to check your work every single time you're doing factoring, that's exactly what you can do. You can just multiply everything back out, and you should get right back to where you started. But that's the method we're going to use. When this a value is equal to a positive 1, we want to just multiply to the n, add up to the middle. Next example, we have two numbers that we want to multiply to a negative 63 and add up to a positive 2. So in some scenarios, it may look a little bit more intimidating than it actually is. Like this one, this looks pretty intimidating because you want 63 and add up to a 2. Like I want it to multiply to a pretty big number, but add up to a pretty small number. If you just think about 63, though, that's only going to be 9 and 7, really, and 3 and 21. So 3 and 21 is not going to work. So that means like, okay, 3 and 21, there's no way that I could add that up to give me a positive 2. So 3 and 21 is not going to work. So that leaves us with 7 times 9. So 7 times 9, where we want it to multiply to a negative, but add up to a positive. So here are our two options. We could have negative 7 times positive 9, or we could have positive 7 times negative 9. And that's when the addition step comes into play. Because both of these scenarios right here are going to multiply to this negative 63, but we want one scenario to add up to a positive 2. So which one is it? Negative 7 plus 9 equals a positive 2. There it is. And if you want to check the other one, 7 plus negative 9 is negative 2. That's not what we want. We want positive 2. So that's the combination of values that are going to work. And since this is x squared, this is going to be x minus 7 times x plus 9. And it doesn't matter. You could write it as x plus 9 times x minus 7. The order does not matter. The sign location does, though. We can't just put the negative with the 9 because that we just didn't think about while we were writing. You know, it has to be in this specific order where we have x minus 7 and x plus 9. But the order of the binomials don't matter. But the location of the negative and the positive do. Because, again, we want it to add up to a positive value and multiply to a negative value. So there it is. Okay, next scenario. Here we want to multiply to a positive, add up to a negative. Where on the last one, we wanted to multiply to a negative, add up to a positive. So in this one, something interesting is going to happen. So let's just think about, all right, I want two numbers that multiply to 35 and add up to negative 12. So 35 really doesn't have a whole lot going on other than 5 and 7. So since I know it's going to be 5 and 7, now I just have to figure out, well, if I wanted to multiply to a positive, how do I have two numbers that are going to multiply to a positive, but then add up to a negative? Well, let's think about that. How do I multiply to a positive? I could have a positive times a positive, or negative times a negative. That multiplies to a positive 35. And then we want it to add up to a negative 12. So if I think, well, 5 plus 7, that gives me a positive 35, so that works. Negative 5 times negative 7 gives me a positive 35, so that works. So let's see which one of these two scenarios disqualifies from being the actual answer because we want to add up to a negative 12. So 5 plus 7 is positive 12. That doesn't work. And don't just think, oh, this one didn't work, so therefore the other one's going to work. Some cases, yeah, that's probably going to be the case. But in some times, neither is going to work, and you might have to use some other methods like quadratic formula or completing the square or something different. Or maybe there's more factors that you're figuring about. But here, if I do negative 5 plus negative 7, that does add up to negative 12. So there is our answer. So it's going to be x minus 5 times x minus 7. That is what that trinomial is going to factor to. Two negatives multiply to a positive, but two negatives also add up to a negative. That's a little bit of a funny error that I see with students where they get so wrapped up in positive or negative is a positive, so then they think, oh, negative plus a negative is going to make a positive. Like, no, with addition, negative 5 plus negative 7 gives us still negative 12. If you're down $5 and you go and you lose $7 more, where are you? You are down $12. Like, you don't all of a sudden get back to positive 12. So that's why it's going to be negative times negative, positive, negative plus negative is still negative. So the last couple scenarios, they've kind of been a little bit more straightforward with we just wanted to multiply to the n, add up to the middle. And we're going to do a couple more examples, but I want to start talking a little bit more about just this process of factoring these trinomials. When you're factoring trinomials, and I'm going to go back to the first slide here, one thing that you want to really be on the lookout for when you start off is looking for a greatest common factor. Now, in these last couple of examples, we didn't really have that. We didn't have a greatest common factor being some sort of factor that I could take out from all three terms. So, for example, if I just had like a problem like 2x squared plus 6x plus 8, just making something off the top of my head, what we notice here is I could factor out a 2. So that is a greatest common factor. I could take out a 2 from every single term. Then what happens is I take out a 2 from all three terms. So 2 divided by 2 is 1, so I'm just left with an x squared there. 6 divided by 2 is 3. And then 8 divided by 2 is 4. So then that would be, we factor out a GCF. And then we'd go through the rest of the steps. And just this example that I made, I don't think we could really factor that using any sort of methods that we've talked about here. We might have to use quadratic formula there, but not the point. After we factor out that GCF, there's actually another step that we can combine with that. So I'll just combine these two together. GCF and then also a leading negative. A leading negative. And what that looks like, let's say we had that same exact problem, but it was negative 2x squared plus 6x plus 8. This negative is the leading term, so a is equal to negative 2. Whenever we have a leading negative, you always want to factor out that negative. So if I take both the GCF and the leading negative, I would have negative 2 being taken out. And that's going to leave me with a positive x squared, because now the signs change. So positive x squared, and then 6 divided by negative 2 would be negative 3x, and then 8 divided by negative 2 would be negative 4. So whenever you have a leading negative, you want to make sure you're factoring out that leading negative. So there's two really rules or scenarios that you want to be on the lookout for when you're factoring trinomials, and these first couple of examples didn't have that, but that's just something that might not always be just this nice clean form. We might have like a negative x squared or GCF that we have to factor out. So let's continue going through some examples here. So here I don't have a leading negative. Like a leading negative again would be like negative x squared, so that means I'd have to factor out negative 1, but we don't have that. No GCF, I'd need like a 2 here and a 2 here, and then this is divisible by 2, so then I could factor out a 2 in that case, but we don't have that. So now this is just ax squared, a is equal to 1, so I could just factor. So I'm going to multiply, I need two numbers that multiply to a negative 42 and add up to a negative 1. 42 is one of those numbers like 24 where there's a lot of combinations of numbers that multiply. So that's just something that takes a lot of practice of just knowing, all right, 42 is this, this, and this, and then I want to add up to a negative 1, so which combinations of numbers work? So when we're going through like 42, the best strategy I always take with a weird number like 42 or just numbers that I'm not super comfortable with, I would just go to my calculator and do 42 divided by 2 and then just get a glimpse of like, all right, so 42 divided by 2 is 21 times 2. So 21 times 2 is 42, 21 plus 2 is 23, 21 minus 2 is 19. That's not going to get me back to 1 in any way because I know I need to add up to a negative. So one's got to be positive, one's got to be negative, and I know I want it to multiply to a negative, so I know the combination has to be positive, negative. So there's no way that I could get this back to 1, so that's not going to work. And then I would just do 21 divided by 3, or not 21, 42 divided by 3. And that's 14. So let's see. So if I had 3 times 14, 14 minus 3 is 11, and that's not going to get us back to 1, so no good there. And then 42, and I know 4 doesn't go into 42, so I'm not going to try 4. And then 5 doesn't go into 42, so I'm not going to try 5. So I do 42 divided by 6, and that's 7. So bingo, I think we have it there. So 6 times 7, 7 minus 6 is 1, or 6 minus 7 is negative 1. So there we know, like, all right, we're going to get negative 1 in some way. Now we just have to figure out what the sign is going to be. Is it going to be negative 6 or negative 7? So we're going to have negative 6 times 7 or 6 times negative 7. Negative 6 plus 7 is positive 1. We want it to add up to a negative 1. That's not going to be it. 6 plus negative 7 is negative 1. There it is, negative 1. So this is going to be x plus 6 times x minus 7. Because 6 times negative 7 is negative 42. 6 plus negative 7 is negative 1, and that's what we wanted. We wanted to add up to a negative 1, multiply to a negative. So it's going to be positive 6, negative 7. The negatives and just numbers like 42, bigger numbers where there's a lot of multiples, that's where people have a lot of trouble. So I would encourage you just to create this little table here, and then that way you could just process elimination. Yeah, it's a little bit more time consuming, but it's a safe route, and you'll find that factor the more you just go through, and you'll get the combinations that work. All right, next one. Here I have a leading negative. Now I don't have a GCF. I don't have any factors that I could pull out, but I do have a leading negative. So in this case, where I have a leading negative, the first thing I'm going to do is take out that leading negative. So I'm going to have negative, and then what happens is I divide each term by -1. I just flip the sign of all three terms. So this is going to become positive x squared minus x, because it was positive x, so it becomes minus x. And this was positive 30, so it's going to become minus 30. And then from here, we just now take our normal methods of factoring, where we want two numbers that multiply to a -30 and add up to a -1. And in some cases, you might factor out a negative, you might factor out a GCF, and then you can't really do anything. Like, you'll have this form, but we can't factor it. Like, there's no combinations of numbers that work. Then you're going to have to use some different methods, like that example that I made just as I was talking about GCF and leading negative. Like this one, we don't have any numbers that would multiply to a +4 while also adding up to a +3. This one would actually work when I factor out that negative, but this one wouldn't. So I have to use quadratic formula or completing the square or something like that. But in this case, let's see if we can go any further. So I want two numbers that multiply to a -30, add up to a -1. So 30 is 15 and 2, 10 and 3, 6 and 5. So just going through this mentally, like 15 and 2, there's no way that I can get back to 1. 10 and 3, no way I can get back to 1. So that's going to leave me with 6 and 5. So I either want -6 times 5 or 6 times -5. And I want it to add up to a negative. So let's see which one works. -6 plus 5 is -1. That's what we wanted. Good. Here's another huge potential mistake that I see. I factor out this negative. The mistake that I see a lot with factoring, when the student takes out a GCF or a negative, they'll just forget about it. Like, it'll just disappear and it will never reappear again. You want to make sure you're tacking that along as you go through the factoring. So what I would do, what I encourage you to do, is I just draw an arrow. Like, okay, this negative, I need to make sure I put this with my final answer, and then you can just ignore it, and then you go through the factoring. So that way I have this visual, like, all right, I got to remember to put this in my final answer, because it's really easy, just like, oh, there's my factors, boom, x, and then you just go through and write your answer, and you forget about it. But this -1 is a part of our final answer, so we factor out that -1, so I can just write this as negative or -1, I'll just write it as negative. And our factors were, what were they? -6 and +5. I almost just grabbed this one because that was the first numbers I saw. Let's just double check. -6 times 5 is -30. -6 plus 5 negative. That's it. So x minus 6, x plus 5. Now this negative here is just as important as all the other factors. Now, if this was equal to 0, if you were solving, then we'd be okay dropping the negative. But if we're just factoring, like, we have to make sure we put that all factors factored completely. So that -1 is a part of our answer. All right, next scenario. Here we have a GCF. I do not have a leading negative, but I do have a GCF. So in this case, since I have a GCF, I want to factor out that GCF. What is the GCF? Well, GCF is the greatest common factor, so the greatest number that goes into all three terms. And the reason I know that there is a GCF right off the bat is because 2, 2, 40, even, even, even. All the numbers are even. So whenever I have all the numbers are even, I know I could pull out at least a 2, if not more. But in this one, it's just going to be a 2. 2 goes into 2, 2 goes into 2, 2 goes into 40. So I know I could pull out at least a 2. And always double check, like, your variables. This is x squared, x. Sometimes there might just be like an extra x here, or x to the third, or something else where you can factor out a variable also. But in this case, we don't have that, so we're going to factor out a 2. Whenever I factor out GCFs, I just divide each term by that GCF. So this becomes 1, so 1x squared. -2 divided by 2 is -1x. -40 divided by 2 is -20. And I know you might be thinking, I thought this video was titled factoring ax squared plus bx plus c when a is equal to 1. Yes, this a value was equal to 2, but I was able to factor out a 2, creating a trinomial with a equal to 1. So we could still use those methods of just looking for multiplication to the end, adding up to the middle. So like I showed here, this is not a equals 1. This is a equals -1. But when I factor out the negative, it becomes a equals 1. And then I think the rest of the examples were just a equals 1. So sometimes there's a little bit of some manipulation in order to get it into the form of ax squared plus bx plus c, where a is equal to 1. So now we want to factor, if possible. So two numbers that multiply to a -20 add up to a -1. So 20 is 20 times 1, 10 times 2, 5 times 4. So 5 times -4, or -5 times 4. 5 plus -4 is +1. We want -1. So we want two numbers that multiply to -20, add up to -1. So that's not going to work. -5 plus 4 is -1. That's what we want. So there it is. Same comment that I made about the negative, factoring out that negative. You want to make sure you're bringing this along for the ride. So this has to be part of our final answer. So the factors that work here were -5 and 4. So x minus 5 and x plus 4. So that is completely factored. Completely factored there. So looking for a GCF on this one. Key. GCF, greatest common factor. Where this one, we had a leading negative. So GCF is a part of our answer, though, so make sure you're writing that as a part of your answer. All right, next one. So this one looks crazy. I see x to the 4th, x to the 3rd, x squared. That's a lot. There's a lot going on here. And I also see 2, 26, 84. All of those numbers are even. So that means I could pull out a 2. And I can't pull out more than a 2 because this is just a 2. There are some cases where we might be able to pull out a little bit higher than just a 2. But in this one, only a 2. So we can factor out a 2. That's what we know, for sure. We can factor out a 2. But what else? I have x to the 4th, x to the 3rd, and x squared. How many x's do all three terms have at least? They have at least x squared, because this one is x squared, x to the 3rd, there's 2 of them that I could pull out, x to the 4th, there's 2 of them that I could pull out. So I'm also factoring out an x to the 2nd. That's a huge possible miss there. I'm just not understanding that concept. Like if I had x to the 3rd plus x, and I ask you to factor out a GCF, and this is just a little side example, you could factor out an x. So that would be x squared plus 1, because I'm taking out the x to the 3rd is 3 x's, and I'm taking out one of them, so I'm just left with 2, x squared. I just had an x, took out, so I just have that coefficient of 1 left over. So in this example, I'm pulling out 2x squared, so that means all three terms are being divided by 2x squared. So what does that result with? 2 divided by 2 is 1. X to the 4th divided by x squared. Little side lesson here. X to the 4th over x squared. When we are dividing by the same variable base, that means we are subtracting the exponent. So it's going to be x to the 4th minus 2, which is x to the 2nd. So I always just do big exponent minus a small exponent. But in most of these cases, like we don't have to worry about where the exponent's going to be because we're factoring out GCF, so it shouldn't really be too much of an issue there. But we're going to get x squared for that first term. 26 divided by 2 is going to be -13. Then we have x to the 3rd over x squared. 3 minus 2 is 1, so we just get x. 3 minus 2 is 1, so x to the 1st. Then 84 divided by 2, it's going to be positive. And this is negative because this was negative 26 divided by positive 2 is still negative. 84 divided by 2 is going to be positive 42. X squared over x squared. There's two ways of thinking about this. Same thing divided by the same thing. X squared over x squared. If I have 2 over 2 equals 1. 3 over 3 equals 1. 4 over 4 equals 1. X squared over x squared equals 1. Or 2 minus 2 is 0. X to the 0, anything to the 0 power is 1. All right, so that was a little exhausting. So now we have to factor still. So we pulled out this crazy GCF of 2x squared, but we still have to factor. And maybe we can't even factor at all. Maybe this is just, the factoring was just taking out the GCF, and then this is its factored form, or we can move forward with quadratic formula. But let's see. I want two numbers that multiply to a positive 42 and add up to a negative 13. If we wanted to multiply to a positive and add up to a negative, that should key right away. Negative and a negative. Negative times a negative is a positive. Negative plus a negative is a negative 13. I talked about that earlier in this video. So 42. What could that possibly be? 42 is one of those difficult numbers where you have a lot of combinations of numbers that work. But for 42, that's going to be 6 times 7 is positive 42. But we want to add to a negative. So negative 6 times negative 7, because negative 6 plus negative 7 is negative 13. So that's going to be my numbers that work. And we make sure we tack on that GCF. So we're going to have x minus 6 times x minus 7. And there it is, completely factored. Yeah, pretty difficult problem there. If you're not catching that GCF, or if you're not catching that this is a GCF of x squared can be factored out, that's going to make things very difficult if you don't catch that. Those very big steps that you want to make sure you're catching. All right, next problem. I have x squared plus 7xy plus 6y squared. So in this problem, it's pretty straightforward on the factoring because we just want two numbers that multiply to 6, add up to 7. But what might throw people off is this y squared at the end. Like, oh my, how do I write in that y squared? What do I do there? How do I figure that out? Can I factor out a y? Like, no, you can't factor out a y because I have a y squared, but I don't have a y here to factor out. So that y is not going anywhere. So here's how we combat that. When I go to write my answer, I know this is going to be x, this is going to be x, right? X times x is x squared. So that I know. What about the y? Well, if I want my last term to be y squared, that means this has to be y, and this has to be y. So whatever I get for my factors, it's going to be x plus something y, or x minus something y, but all I know is this is going to be y times y because I want it to be y squared at the end. So now we just have to deal with the 6 and 7, and I don't need to write, I want two numbers that multiply to 6y squared and add up to 7x. Like, I don't need that. I'm just worrying about the coefficients. So I want two numbers that multiply to a 6, add up to a 7. 3 and 2, 6 and 1, it's going to be 6 and 1. So 3 times 2 is 6, but 3 plus 2 it does not add up to 7. So it's going to be 6 and 1, positive, positive, don't have to worry about signs. So x plus 6y, x plus 1y. And I can just leave it as x plus y also. I don't have to write in the 1y, the x plus y is the same thing. But yeah, this is just, don't let some weird variable completely throw you off, make you feel like you don't know what's going on. It's just, how do I get that to be y squared? Y times y. So y times y would give us that y squared there. Last problem that I have in this video, this is a scenario that's called a perfect square trinomial. So the reason I'm pointing this out is because it actually has like a form, like, oh, this is a perfect square trinomial. It doesn't really change anything though. It doesn't change our methods. It doesn't change the process. It's just like an identification of like, this is a perfect square trinomial. So that means that I could write this a little bit differently. So let's just factor this normally. So again, no greatest common factor, no leading negative. So that means I want two numbers that multiply to a 16 and add up to an 8. 16 is 8 times 2, 4 and 4. 8 times 2 is not going to work. So 4 times 4 is 16. 4 plus 4 is 8. So here's where that perfect square trinomial means. 4 times 4. So what we would have is and they're both positive, positive and positive. So x plus 4 times x plus 4. Same factors. So what a perfect square trinomial can be rewritten as is x plus 4 squared. That's what a perfect square trinomial tells you, that since they're the same, I could just write this as x plus 4 squared. Now, is this wrong compared to this? No. Like, these are both completely correct answers. I don't see any issue with just leaving it as x plus 4 times x plus 4. There are scenarios where understanding solving some scenarios where you might need to write it in this form in order to move forward. But in terms of just factoring this trinomial, we are completely fine with either form. And that's why I'm just throwing this on at the end of this video, just to show you, like, hey, this is actually something. It's called something perfect square trinomial, where you could write it as x plus 4 squared. And that only happens if you have the exact same terms. Plus 4, or minus 4, perfect square trinomials. So I hope this video was helpful to you in factoring all forms of a equal to 1, and I want you to just make sure you notice that we did a couple problems here where the a started off not equal to 1, but we did some methods, leading negative, GCF, that created a trinomial in the form of a equal to 1. So then we were able to move forward with just this straightforward method: multiplication to the end, addition to the middle. So thank you for watching.